Today's notes are about our last conic section in this unit. They are known as hyperbolas. The definition of a hyperbola looks very similar to the definition of an ellipse, except for that one word that I wrote in capital letters. If we're given 2 points, A and B, and those are still known as the foci, a hyperbola is the set of points P such that the difference in the distances PA and PB is constant. So PA minus PB is always some value that's going to be the same. So remember, in the ellipse, it was the sum of the distances were constant. Here it's the difference, but A and B are still called the foci. We're going to talk about what the equation of a hyperbola looks like. And let me write out what it could be. X squared over A squared minus Y squared over B squared equals 1. This is one type of an equation you might see that would represent a hyperbola. Notice what's different about this equation and the equation for an ellipse. There's actually only one major difference, but it's just a small, it's something you might not notice right away. We are subtracting our two terms instead of adding them. So if you remember for the ellipse, that sign in the middle was actually a plus sign. Here it's a minus sign. Because we're subtracting, the order in which we see x squared and y squared terms is important. That is not the same equation as this, y squared over b squared minus x squared over a squared equals 1. So that's why I have 2 sketches of blank axes underneath. We're going to look at what the difference in the picture looks like when the x squareds come first versus when the y squareds come first. Because we're subtracting, they're not the same thing. Notice that in both cases, though, we are always equal to 1. So that is a similarity between a hyperbola equation and an ellipse equation. If you remember in class, we talked about when we slice a cone, how we generate the hyperbola. We have those 2 branches, those 2 arms, because we've hit part of the positive part of the cone and part of the negative part. So in this first example, x squared over a squared minus y squared over b squared equals 1, we are going to get x-intercepts, and these are both centered at 0, 0. And we have these 2 branches, and they kind of look like this. So this is a rough sketch just showing the orientation of a hyperbola that has the equation in that form. The other hyperbola, where the y squareds come first, is going to have y-intercepts instead of x-intercepts. So our hyperbola might look something like this. I haven't talked at all about how I know how wide the arms are, and that's going to be easier to see when we have a non-general example, so we'll see that a little bit later. But I just wanted to show you the general shape and how we know if it's opening left-right versus up-down. It's opening left and right if our x squareds come first. It's opening up or down if our y squareds come first. So it's something extra we have to pay attention to. The other added part of a hyperbola is because we've sliced through a cone, the ends of the hyperbola are approaching linear functions. What that means is we actually have 2 asymptotes in every hyperbola. Here's one, here's the other. We talked about how the branches of a hyperbola, you might accidentally think that they look parabolic, like parabolas, but they're actually not. They are approaching lines way off at the end. They're approaching kind of the axes of the cone that we sliced through. So for this second hyperbola, the asymptotes would be here and here. So now you might be wondering, how do I find the equations of those asymptotes? And in general, the asymptotes of our hyperbola are at y equals b over ax, and remember there's 2 of them, y equals negative b over ax. We know what a and b are from our equation, and that should make sense that that is the equation of a line. Slope times x plus your y-intercept. But before we shift these hyperbolas around, our y-intercept of all of our asymptotes is at 0. So it should make sense that we have a y-intercept of 0. We're going to see in our next example why our slopes are b over a and negative b over a. Let's try to graph this hyperbola. X squared over 9 minus y squared over 36 equals 1. First thing I want to note is that what's underneath the x is a squared, and a is then going to be 3. B is going to be 6. Right? Notice this is not shifted, so our center is at 0, 0. I want to think about that. And what we're going to do to graph this is actually start out kind of like we did for the ellipse. I'm going to go 3 left and right in the x direction and just kind of mark that point, and 6 up and down in the y direction and mark those points. Now if this was a plus sign in the middle and it was an ellipse, I would connect those with the rounded shape and be done, but because it's a hyperbola, I have to be careful about what I do. We are going to create what is known as the central rectangle. This central rectangle is going to help us get an accurate shape of our hyperbola. So notice how I'm creating this rectangle. I'm making it the same width. I'm going twice that A value is the width and twice that B value is the height. I'm making sure that the sides of my central rectangle are going through those points that I've marked. The reason that this rectangle helps us is I can now easily graph the asymptotes. The asymptotes go through the center and the corners of that central rectangle. If I hadn't graphed in that central rectangle, I wouldn't know where the corners were, and I wouldn't know how to graph the asymptotes. I wouldn't know how steep the asymptotes were. Now I have enough information on my axes to be able to graph the hyperbola. The x's come first, so there are x-intercepts here. The intercepts lie on the sides of the central rectangle. So those 2 purple points are the x-intercepts. All I have to do now is make my hyperbola by drawing in the branches. I want to make sure the vertex is on the side of the central rectangle and that the arms extend and approach those asymptotes as we move out. The name for those first 2 points that I graphed are the vertices. So I can say that the vertices here are at 3, 0 and -3, 0. We don't have co-vertices in the hyperbola because we just have those 2 branches. It should now make sense why the slopes of our asymptotes were b over a, rise over run. The rise is always our b value, what's underneath the y. The run is our a value, what was happening underneath the x. So the equations of our asymptotes are y equals b over ax, and this a similar line but with a negative slope, y equals -b over ax. Now of course 6 over 3 is just 2, so why not simplify? Y equals 2x and y equals -2x. Our last thing that we're trying to do here is write the domain and the range. Our domain is -infinity up to that first vertex, -3. We are including that point, though, because it does exist on the graph. Union 3 to infinity. Notice there was kind of this space in between those 2 branches where we had no inputs. Our range is -infinity to infinity, low to high. There was never a break in our range. So the green, everything in the green was just kind of a framework to help us graph, but the actual picture is the purple. Let's do one more example. Y squared over 16 minus x squared over 25 equals 1. I'm hoping that you notice that the major difference between this equation and the previous one is that here the y squareds come first. I'm still going to call a what's underneath the x, so we'll say a is 5 and b is 4. If we always let a squared be under x and b squared be under y, then the equations of our asymptotes are always b over ax and -b over ax. So that's why I'm keeping my variables defined that way. Let's see, we're not shifted, so our center's at 0, 0. We're going to go 5 out in the x direction, either way, and 4 up and 4 down in the y direction, and graph my central rectangle. There we go, making sure that the sides go through those points that I've marked. I'm now going to sketch in the asymptotes going through the center of the central rectangle and the corners of the central rectangle. Again, without that central rectangle, I wouldn't know how steep to make those asymptotes. Now we see since the y squareds come first, we know that it's going to open up and down. It's going to have y-intercepts. So our vertices are at 0, 4 and 0, -4. I can now sketch in my branches. I can do a little bit better than that. Based on where I placed the vertices. and where the asymptotes are. There's our hyperbola. Again, the hyperbola is just the green part. The purple part was helping us graph it. The asymptotes are y equals, let's see, b over a x, and y equals negative b over a x. Can't reduce 4/5, so we're done with our asymptotes. Domain this time, if I look left to right, there's no break, so it's negative infinity to infinity. The range this time, if I look low to high, there is a break there. So we're negative infinity up to -4, including that point, union 4 up to infinity. Take note that the two examples we did in this video were both not shifted. They both had a center at 0, 0. Once we shift these, of course our center will change, and also the equation of our asymptotes will be shifted as well. But we'll see possible examples of those in class. Good luck!